Okay, so we just did this problem here uh, where we had these probabilities assigned to the elementary events, and then we figured out the probability of some other events, E, G, and H. We noted earlier that probabilities may be assigned to elementary events either by logical reasoning or by using experimental data. Probability models obtained by logical reasoning are called assumed or a priori models. So a priori means like before experiment or before experience. So they're called assumed or a priori models. And those obtained from experimental data are called empirical or a posteriori models. So those are ones that are done after experiment. They're also called empirical. The simplest a priori models occur when the experiment has finitely many outcomes, all of which have equal chances of occurring. We now study such models in detail. So now we're going to talk about experiments with equally likely outcomes, because those are the simplest ones to deal with. In many experiments, there's a certain symmetry or uniformity among the sample points that suggests that all sample points have the same chance of occurring. Such sample points are called equally likely, and the outcomes are said to occur at random or randomly. So when you toss a fair coin, by fair coin we mean equally likely outcomes. A fair coin, in other words a balanced coin, is one that is perfectly balanced with a head on one side and a tail on the other. If we toss a fair coin, it is reasonable to assume that heads and tails are equally likely. A fair die is perfectly symmetric and perfectly balanced cube with faces labeled 1 through 6. If we toss a fair die, it is reasonable to assume that the 6 possible outcomes are equally likely. If we pick a name at random from a list of 8,000 different names, when we say at random, we mean each of the names has the same chance of being selected as any other name. By definition, the randomness of the 8,000 outcomes indicates that they are equally likely. So the fact that we say random means that all of them are equally likely. If an experiment has k equally likely sample points, so this one we would say has 8,000 equally likely, this one we would say has 6 equally likely, this one we would say has 2 equally likely. So if an experiment has k equally likely sample points, then we assign each sample point the same probability, if they're equally likely. Moreover, since the probabilities of the sample points must add up to 1, the probability of each sample point must be 1 over k. So if there are k of them, each one must be 1 over k probability. Thus we have the following result. If the sample space for an experiment has k equally likely sample points, then each elementary event should be assigned probability 1 over k. This assignment of probabilities, so this is an assignment of probabilities, this is a way of assigning the probabilities, and this one is called the uniform probability model. So when they're all assigned, when all the sample points have the same probability, it's called the uniform. Uniform means the same. The uniform probability model for the experiment. Remember, we could assign it in a non-uniform way. That would be a different model. But if we assign them all the same, it's called the uniform probability model. So if we're talking about the uniform probability model for a fair coin toss, it's going to be 1/2 and 1/2. If it's for a fair die, they're all going to be 1/6. And then the other example 6 before, was not uniform, since the elementary events probabilities were not equally likely. If a card is picked at random, there's that word, at random, from a standard deck of 52 cards, what is the probability that the card selected is the ace of spades? So that's 1 out of the 52 cards. If they're all equally likely, then the probability is 1 over 52. But let's read it. Since the card is picked at random, all possible selections are considered to be equally likely. Since there are 52 different outcomes for this experiment, each has probability 1 over 52. Thus, the probability of picking the ace of spades is 1 over 52. If an experiment has a uniform probability model, that means all the elementary outcomes are equally likely, then the probability of any event can be obtained by, then the probability of any event, not just the elementary events, can be obtained by counting sample points. To be specific, suppose that the sample space has k points, and E is an event with m sample points. So m is supposedly S sub n, m is supposedly less than k, right? Because you can't have more elements in the event than are in the sample space. Okay? Since the sample space contains k equally likely outcomes, each sample point has probability 1 over k. Thus, by the addition principle, the probability of E is going to be the probability of this, plus this, plus this, plus this, plus, and so on. So that's what they have here. But each of these is 1 over k, so it's 1 over k for each of them, but there are m of them, so it's m over k. There are m terms. Therefore, we have the following result. If an experiment can result in any one of k, and we have to say, in this case we're talking about equally likely outcomes, so the uniform probability model, and if an event E contains m sample points, then the probability of E is m over k. It's the number of sample points in E divided by the number of sample points in the sample space. In other words, it's n of E over n of S. Now this is for a uniform probability model situation. So using that, if E is this, the probability of E will be the number of elements in E divided by the number of elements in the sample space, so it's 3 over 6. If this is G, then the probability of G is going to be the number of elements in G divided by the number of elements in the sample space. So it's going to be 2 over 6. Okay, if a pair of fair dice is tossed, what is the probability that the sum of the numbers tossed, the sum of the two dice, is 7? Okay, so assume one die is red and the other is green. Label the dice R and G. Each die can show one of the integers 1 to 6, so that the two dice can yield any one of 36 pairs in table 4. So in other words, this is the sample space. We can have the green die like one of these 6, and the red die is one of these 6. So one possibility is 1 on the red die and 1 on the green die. Another one is 1 on the red die and 2 on the green die, and so on all the way through. We have 6 rows and 6 columns, so that's 36. What is the probability that the sum of the numbers tossed is 7? So the sum of the numbers tossed is 7 must refer to some event, because we only say what is the probability of an event. So this is some event. So which event is it? That means which subset of the sample space is it? So you can see which subset it is. It's this. The subset contains this, 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 and this. All of those are the only ones that add up to 7. So it's this subset here. Okay? So if we want to know the probability of that event or that subset, since these are all equally likely, that's what we said, so each one of them, so then we can use the rule that says it's the number of elements in the subset, the number of elements in the subset divided by the number of elements in the sample space. So there were 6 elements there that I just pointed out, and there are 36 in the sample space, so it's 6 over 36, or 1/6. So the probability that the sum is 7 is 1 over 36. Okay, you can stop and read this one. You can check how to find the outcomes by going through this table, HH. Well, I'll say, if you want to do 2 coins, you say the first coin and the second coin. You just make a little dot here and write start, and then you say, for the first coin, what can happen? You have 2 possibilities. You can have H or T, and then once you have H, you can say, what are the 2 possibilities? You can have H following the H, or you can have T following the H. And if it's T here, you can have H following the T, or T following the T. So that the possibilities are HH, HT. You just follow out the path, TH, and TT. So these are the possibilities.